Welcome back to the latest lecture session. We started discussing about hard water that causes issues when we are trying to use it, right? Boilers, scaling is the primary issue. When we are talking about scaling, we are talking about precipitation of calcium carbonate or magnesium, right? Calcium or magnesium. So, when I am concerned about removing these aspects, we are typically going to add lime or soda. So, I am going to soften the water by adding lime or soda. So, that is why we call it as or refer to the process as lime soda softening. In this aspect, or we looked at some basics because we are going to use them later. So, we know that acids can dissociate to form bases, thereby releasing H plus. Yes, and we know that the systems can be in equilibrium. Yes, and we also know that different products or different solids can be formed. And we also saw how to write the equilibrium constant for different equations, let us see, right. For example, in this context we saw that activity of the relevant solid is 1, assuming that it is a pure solid, and that is why we do not use that in the equilibrium constant. And in this class we are also going to use activity or concentration instead of activity, assuming that the ionic strength is relatively less, let us say. So, this is what we covered in the previous session. So, let us see what else we are going to look at. So, what class is it when we consider the water as hard? So, when the water is 100 to 150 milligram per liter, that is when we are concerned with hardness, right. And in general, I think Roorkee, we looked at the relevant values, it was 250 or so. So, it is typically hard and different, what do we say, deposits upstream. So, above Haridwar or upstream of Haridwar compared to the flow of the Ganga canal, the water can be extremely or very hard, let us see. So, we see that hardness again is an issue at most places, and I think in the south, it's at least depending upon where you are, the hardness is remarkably high, right. So, what does, with respect to drinking water, what does it say? At least the Indian standard says that 200 to 600 milligram per liter expressed as CaCO3. Even here, note that the units are expressed as CaCO3. So, this is one aspect I will discuss. Let me come back to that. So, here we see that first our Indian standards are pretty lax in this case, but in general, if its water hardness is greater than 250 milligram per liter as CaCO3, right, you are going to have issues. So, maybe for drinking too it is not good, assuming this looking at this 600 what do we say, TDS2. So, in general 250 is what you should aim for, but this is what the law says, let us say, that is acceptable. But again, that is some background for you. For example, in the US I think it is around 40 or 60 typically, right. That will give you an idea about the hardness that people try to achieve in different countries. So, in this context we started coming across some term, right. What is this? Hardness or this unit milligram per liter as CaCO3. I am assuming we might have discussed this in this course elsewhere, but nowhere is it more relevant than when we discuss hardness. So, here I am talking about hardness due to calcium, hardness due to magnesium, right. So, I can't always keep talking about what is the concentration of calcium, magnesium when I talk to some person about the hardness of water. So, there has to be some metric or some equivalence which will let me capture the hardness that will be caused by these two particular cations, bivalent cations. So, that which is often used is expressing the units as milligrams of CaCO3 per liter, let us see, milligram per liter as CaCO3. So, let us see what is the approach here. In general, let us say I have milligrams of Ca2 plus per liter, x milligrams, let us say. So, if I divide by the molecular weight, what will I get? I will get the moles, as in I know for 1 mole of Ca2 plus, right, I think 40 grams of Ca2 plus, right, that is the relationship, 40 grams per 1 mole. So, why did I write this here? In general, I am not great at dividing, multiplying and such, but I always look at the units. If I want the units of moles per liter, let us see, right. If I want the units of moles per liter, I obviously need to remove this mass of calcium. So, for that I need to have mass of calcium in the denominator. So, that is how I write it in this way, let us see, right. So, now I have the units in terms of moles per liter of calcium, but I am not concerned about having or understanding just moles of calcium and moles of magnesium and such, right. I want to have some equivalents or some equivalents which will give me an idea about the total or all the calcium and magnesium present there. So, that is, as I mentioned, typically you expressed in terms of CaCO3. So, how do I go from moles of calcium to milligram per liter of CaCO3? Here the key is to understand that equivalents in this context are with respect to the charge, right. Equivalents can be with respect to the electrons being transferred, right, and H plus being transferred, or with respect to the charge or the valency. In this case, it is the charge. So, Ca2 plus, obviously, as you can see, it will have 2 equivalents per 1 mole, right. So, for 1 mole of Ca2 plus, 2 plus charge, right. So, 2 equivalents will be contributed. So, now I have the units in terms of equivalents. It is no more in terms of Ca2 plus or any such aspect, it is just 2 equivalents per liter. Why? These moles per liter and moles per liter will cancel out, but still how do I come to as CaCO3, let us say, right. So, here the aspect to note is that when I add CaCO3 to water, it will become either Ca2 plus or CO3 2 minus. So, if I am concerned with positive charge, again 2 equivalents. If I am concerned with negative charge, again 2 equivalents. So, even here for 1 mole of CaCO3, 2 equivalents will be what do we say given out. Here we are talking about the charge, and 1 mole, again looking at CaCO3, I guess, right, 40 plus 12 C calcium, carbon, and 16 into 3 48. So, I guess that is 100 grams, right, that is the molecular weight. Yes. So, for 100 grams of CaCO3, it is 1 mole, right, 1 mole. If I multiply this, let me change the color so that it is easier to understand what I am talking about. So, this is where we are. So, if I look at this, what will this turn out to be? Yes. So, I am going to cancel out moles and moles. So, I will have 50 grams of CaCO3 per equivalent. So, this is called the equivalent weight. So, that is something you have to keep in mind, let us say, right. So, now I have this in equivalents and I want the units in terms of CaCO3. From here or using this information, I can now transform these equivalents and get to grams of CaCO3. So, what do I need to do? I will need to multiply by 50 grams of CaCO3 per equivalent. So, now what are the units in terms of? Let us just check, right. So, as we see, this mass term and this mass term cancel out, and then this moles term cancel out, these equivalents, right, cancel out. Obviously, mass of calcium you can only cancel out with mass of calcium, right, and moles of calcium only for moles of calcium, but equivalents here it is with respect to charge. So, equivalents and equivalents you can cancel out here, and then here what are the units finally? It is as grams of CaCO3 or mass of CaCO3 per liter, which is always here. So, now we see how we can transform the units from one particular mass units of calcium to express them in terms of CaCO3. Let us just see what it entails. We started with x. So, it is 2 by 40 into 2 by 40 into 50, let us say, right. This is for calcium though, keep that in mind, right. So, what do we have here? This is 20. So, 2.5 I guess, right. Hopefully, I made it right. So, for x grams of Ca2 plus per liter, it will turn out to be that I need to add 2.5 times x grams of CaCO3, right, or when I add 2.5 x grams of CaCO3 per liter, I will end up getting x grams of Ca2 plus per liter, right. So, in essence, I am expressing the units of Ca2 plus and how much CaCO3 equivalents it's going to be, right. So that's the relevant aspect, let's say. Yes. Okay. So if I made any calculation errors here, that you can look it up, but you see the approach, same case you can do that for magnesium, let's say. So 2 or 3 aspects to take away here. The equivalent weight of CaCO3 is 50 grams. So that's something to keep in mind. The equivalents we are talking about are with respect to the charge, let's say, right. So that's something that you will always have to keep in mind. So we are going to look at this or use this quite often. As you can see, you know, everything in this context of hardness or such is expressed as CaCO3. That's something to keep in mind. So that's enough discussion about changing from one units to the other. So conversion to CaCO3 units, let's see if we have an example here. So we have different ions here and we want to convert them to CaCO3 or as CaCO3 units. So what is the approach everywhere? So we just looked at that. So if we have milligram per liter of a particular compound Ca2 plus, first I am going to divide it by the molecular weight, 1 mole of Ca2 plus and grams per grams of Ca2 plus, right. Then I will get it in moles, and then I know that it's 2 equivalents per 1 mole of Ca2 plus. Why is that? Because it's the charge. Here it's 2 plus, pardon me, difficult to write with this pen, I guess. Yes, so this is Ca2 plus. So now I have it in terms of equivalents. Then if I multiply that by 50, which is the equivalent weight, 50 grams of CaCO3 per equivalent, let's say, right. So that's when I'll get the units in terms of as CaCO3. So it will be the same case with everything else or all the other ions. Only thing we are concerned about is the charge. Here it's 2 plus, and here it's plus. So this means 1 equivalent per 1 mole, and here it's negative, again only 1. So 1 equivalent per mole, here it's again 2. So 2 equivalents per mole, 1 equivalent per mole, and all the relevant mass is given out here. So let's see where we have or what we have. Okay, so again we understood it in detail, but you know, so that it's presented in a better manner, I guess we are going to look at it. So number of millimoles equal to given concentration by molar mass, but again I am not always comfortable write it in this way and understanding it. I at least have learnt that the way that I write here is easier for me, at least, because then I can see what to cancel out or what to divide or multiply with, let's say, right. So that's something for you to consider. If you are more comfortable with this approach, that's fine, obviously. So number of millimoles, given mass concentration by molar mass, given concentration, if it's in mass, let's say, given mass concentration. So number of milliequivalents equal to number of millimoles into valency. Milligram per liter as CaCO3 will be equal to milliequivalents into equivalent weight of CaCO3, and equivalent weight of CaCO3 is the molecular weight, which is 100, divided by the valency depending on the charge, whether it's positive or negative, Ca2 plus and CO3 2 minus, both 2. So that's why 2 here. So that's 50 grams, let's see. 50 grams is the equivalence, let's say, or the way I write it, it is 50 grams of CaCO3, always write the compound per equivalent. So that's something to keep in mind. So now what do we see? Here we have the molar mass 40, 24, 23, 61, 96 and 35.5. Then the valency 2 charge, thus 2, 2 charge, thus 2, 1 charge, thus 1, 1 negative charge, thus 1. Here we are concerned with the magnitude, not the positive or negative, right. And 2, that's why 2, minus 1, that's why 1, let's see. Millimolar units, we know how to get that, I guess, divided by the molecular weight, so that you can get the units in terms of moles per liter, right. So that's something that we have, and we already have the equivalents. You will have to multiply that. Yes, again this is the approach that we talked about earlier, and then you will have it in equivalents. And equivalents, you know that the equivalent weight of CaCO3 is 50 grams per equivalent. So I will have to multiply it with 50, and what do I get? I will get this, right. So let me write it down at the bottom for calcium. So I have milligram of Ca2 plus per liter. How many milligrams? 103. First I will need to convert it into moles. So if I want moles in the numerator, moles of Ca2 plus, I will write that. So I see I need to cancel out the mass, so I will have to write the mass. So mass will have to be the molecular weight, which will give me the relationship between moles and the mass. So, I see that it is 40 grams of Ca2 plus will be required to give 1 mole of Ca2 plus, right. And I know that I need to convert it into equivalents, let us see. So, how do I do that? I see that Ca2 plus has a charge of 2. So, for each mole, for 1 mole of Ca2 plus, I know that I will have 2 equivalents. Here obviously, even though I do not write it down, it is equivalents with respect to charge. And then I already know that 50 grams of CaCO3 will be required for 1 equivalent in terms of charge, and then I will get my answer, I guess, right. So, I think last time we saw that it was around 2.5 times. So, I think 103 to 2.5. So, that is more or less it. So, in the same way you can calculate it for the different other compounds and you will get the relevant units expressed as CaCO3. In general, maybe for SO4 2 minus and for Cl minus, it does not make much sense to express them as CaCO3, but there is a reason why we do that. We can look at that later. But obviously, for calcium, magnesium and HCO3 minus, it makes much sense to express them as CaCO3, let us see, or in equivalents of CaCO3. So, let us move on. So, this is a shortcut. Again, I typically do not like this because shortcuts you need to mug stuff up. For total hardness as CaCO3. So, divided into the carbonate and hardness and non-carbonate hardness, we will come back to that later. But what is the total hardness is equal to the sum of the bivalent concentration, this is the concentration, right, of the bivalent cations into 50, which is the equivalent weight by equivalent weight of this bivalent cation, right. For example, for Ca2 plus, earlier equation, if what is the hardness here, let me, and they want it in terms of as CaCO3. How do I do that? Sum of Ca2 plus concentration, I think 103 milligram per liter, and equivalent weight of this thing Ca2 plus 40 grams is the molecular weight, by 2 is with the valency, right. So, that is going to be equal to by 20 into 50 is the equivalent weight of CaCO3, right. So, it is more or less like for 20 equivalents or 103 milligram per liter, 20 equivalents for 50 equivalents, how much, I guess. So, that is how you do it. This is for calcium, and for magnesium, what is it like? We see it is 5.5 milligrams per liter by 24 by 2, that is 12 into 50. That will give us an idea about the relevant hardness, let us see, right. Here obviously, the units are in mass units. Again, this is one reason why I do not like this way, but again that is something to keep in mind. So, this is the total hardness. And what is this new term total hardness, and why am I having to classify it further into this carbonate hardness and non-carbonate hardness? So, it depends on how easily you can remove it. So, carbonate hardness, typically you can remove it, or it is the hardness that can be removed if you are going to be able to, what do we say, heat up the system, right. This is just for classification purposes, but we will see why it is relevant later, right. So, carbonate hardness, that which can't be removed when you heat up the water, you are going to call non-carbonate hardness. This carbonate hardness is typically the one associated with magnesium, right, typically, and calcium too, some of it, but again we are saying carbonate hardness, we will look at why, or maybe I should explain it now. The carbonate hardness, the concern is that, as you saw earlier, we can precipitate out calcium in the form of, or one of the forms calcium precipitates out is CaCO3, right. And what is this going to be dependent upon? If I have Ca2 plus, how can I go from Ca2 plus to CaCO3? What is the other compound that is missing? So, I need to add CO3 2 minus, right, or need to have CO3 2 minus. So, if I have enough CO3 2 minus, right, this reaction, or by increasing CO3 2 minus concentration or Ca2 plus concentration, I can go to the right and precipitate out the solid. So, if I have enough carbonates, again that is relatively easier to remove. Maybe that is one reason why they call it as carbonate hardness, but in general the textbook definition and such is that if you heat up the water and you can precipitate out certain forms of carbonate or magnesium, that which precipitates out is called carbonate hardness. That which does not precipitate out is called non-carbonate hardness. That is the relevant definition or understanding, I guess. So, carbonate hardness, which is also called temporary hardness, because when the water is heated, the insoluble carbonates will precipitate and tend to form deposits in the water heaters. This is one particular way that it occurs. But again, Ca2 plus HCO3 minus, but in effect it will have to be CO3 2 minus, will go to CaCO3, the solid. This is indicating that the solid is precipitating, let us say, right. So, that is something to keep in mind. So, this is for carbonate hardness, but in general also you will have some due to magnesium, especially when you are concerned about what do we say, precipitation in boilers, let us say, right. This is the carbonate hardness. Non-carbonate hardness, obviously if there is a total hardness and if you can measure what is carbonate hardness, the non-carbonate hardness is going to be the remaining part, let us say, right. So, that is pretty much it. So, let us visualize it and understand. This is obviously the key aspect. So, I have different anions and cations. In this aspect, obviously if I want to use or present them in a bar chart, I can't just have milligrams of calcium, milligrams of Cl minus, right. Then there is no way to compare the equivalents. So, here we are talking about charge, and in water always you are going to have charge neutrality, as in all the cations present are going to be equal to the equivalent concentrations of all the anions present. Equivalents of all the cations equal to the equivalents of all the anions. That is the charge balance. There will never be charge imbalance, let us say, right. So, here obviously we are going to have to look at equivalent units, and that is one reason too obviously why we will express units in terms of as CaCO3, let us see. So, now you understand why even Cl minus we express as CaCO3. Again, that is an different aspect. So, here or in this figure what do we see? We see that the relevant cations or positively charged ions are only due to calcium and magnesium, and relevant anions or the negative charge is due to bicarbonate and Cl minus, let us see. Obviously, as I mentioned, charge balance has to exist, that is why the sum of the cations is equal to the sum of the anions, let us see. That is something to keep in mind. And next aspect, what do we know the total hardness to be? It is equal to the sum of all the bivalent cations. In general, we are concerned about calcium and magnesium. So, Ca2 plus Mg2 plus. So, that is why we have total hardness encompassing the concentration of Ca2 plus and Mg2 plus. So, next, what is this carbonate hardness about? In general, it will depend upon the amount of CO3 2 minus present, because I told you in the form or told you about the form it will precipitate out, let us say, when it is heated and such. So, in general, carbonate hardness, it depends upon the amount of carbonate present. So, obviously, carbonate hardness will be equal to HCO3 minus present. So, that is what you see here, carbonate hardness, let us say. And the remaining part obviously is going to be the one associated with non-carbonate hardness, yes. So, carbonate hardness, when we are measuring, we are going to see to it that we look at the carbonates that are present typically, or the alkalinity at pH 7. We will come back to that alkalinity and such. In the second figure, again for a different water, here we have other cations and but only one anion, let us say. Rarely the case, these are all hypothetical cases. And one aspect to keep in mind that in general in water, you will never have the data for all the cations and anions. That is going to be impossible to measure. Again, that is something I wanted to mention, pardon me. So, here again we have charge neutrality in this hypothetical water. We have all the cation equivalent concentrations being equal to the sum of the equivalent anion concentrations. So, total hardness is what we say now, the sum of calcium and magnesium. So, that is why you see this, yes. And carbonate hardness is the one associated with HCO3 minus, but obviously the carbonate hardness can't be higher than total hardness, right. It can't just blindly be HCO3 minus, yes. So, here carbonate because alkalinity or the carbonates are higher than the total hardness, right. The concentration of the carbonates or the bicarbonates are higher than the total hardness. We are going to say that carbonate hardness is equal to total hardness, and there is no non-carbonate hardness, right. So, that is something to keep in mind. So, here when understanding the amount of carbonate hardness, what am I concerned with? I am concerned with the amount of carbonates present in the form of CO3 minus or CO3 2 minus, let us say, right. So, that is something to keep in mind. If it is less than, then carbonate hardness will be equal to the alkalinity or the bicarbonate. Here I am using this term alkalinity. I know we discussed this earlier. Alkalinity is the acid neutralizing capacity. So, if I list the, and if we look at standard methods, it will tell you about the amount of acid required to bring down the pH to around 4.3 or 4.5. So, I will have to add acid and see how much acid the system or the water will consume before the pH comes to 4.3 or 4.5. So, what will it consume? It will H plus. What can it be neutralized by? It can be neutralized by those bases that are in that particular system. Typically, we have only the carbonate system. So, the bases, other bases are OH minus, carbonate system bases HCO3 minus and CO3 2 minus. Since CO3 2 minus can neutralize 2H plus, we will have 2 equivalents here and obviously minus H plus, let us say, right. So, this is the equation for alkalinity, but knowing that your particular system for carbonate alkalinity, I think we discussed this earlier, right. It is going to be something like this. This is H2CO3, this is HCO3 minus and this is CO3 2 minus. As you can see at around pH 7, as I told you pKa is 6.3 and at around or near the neutral pH of water, which is pH 7, right. You can see that there is no CO3 2 minus, CO3 2 minus is almost 0 and at pH 7 OH minus and H plus cancel out. So, in effect almost all the alkalinity when the pH is near neutral is equivalent to the concentration of HCO3 minus. So, that is why I was using the terms interchangeably when I talked about HCO3 minus or alkalinity, right. So, this is something we will look at in the next slide. So, let us just understand the relevant aspect. If total hardness, right, calcium and magnesium is greater than alkalinity, in general you know the alkalinity equation, but you also know that at neutral pH for general water systems, alkalinity and concentration or alkalinity which is in equivalents per liter will be equal to the concentration of HCO3 minus. We saw that why that is the case in the previous slide, let us see, right. So, if total hardness is greater than alkalinity, let us say, then obviously carbonate hardness will come into the picture, yes, and that is going to be less than the total hardness, right. Let us see what I have. So, carbonate hardness will be equal to the alkalinity, yes, and non-carbonate hardness will be equal to the difference between total hardness and carbonate hardness, and that is the same thing that we saw out here, let us see, right. And let us move on. And if total hardness is less than alkalinity, this is relevant to the second picture that we saw there. We see that carbonate hardness will be equal to total hardness and non-carbonate hardness will be equal to 0. This was the picture I think where we had some Ca2 plus, some Mg2 plus, some Na plus and everything else was HCO3 minus. Total hardness is this and alkalinity, which is in effect HCO3 minus concentration, which was given in the previous slide, was equal to this. Obviously, carbonate hardness can't be greater than your total hardness. So, that is why total hardness equal to the carbonate hardness and non-carbonate hardness is 0, right. That is something to keep in mind. Let us see, and what is the case if calcium is greater than alkalinity, right. We have HCO3 minus, right. Then here now we were looking at carbonate hardness and non-carbonate hardness. Now we are going to start looking at calcium due to carbonate hardness or calcium non-carbonate hardness, magnesium carbonate hardness, magnesium non-carbonate hardness. First, why do I need to understand this or even the previous aspects? Because the way that I am going to remove calcium or magnesium depends upon the type of, what do we say, ion that it is associated with when we talk about hardness. Let us say, is it carbonate or non-carbonate hardness? That is why I need to be able to understand whether it is what do we say, carbonate or non-carbonate hardness. So, if calcium is greater than alkalinity, right. So, if calcium is greater than alkalinity, what will we have? Calcium carbonate hardness will be equal to alkalinity, right, and calcium non-carbonate hardness will be equal to the total calcium concentration, let me say Ca total minus the Ca, calcium carbonate hardness. Let me draw a figure that maybe will help us in this manner. So, the Ca2 plus itself is greater than, and this is Ca2 plus and this is Mg2 plus. So, for this the picture you can look at the previous slide, picture 1 on the left and this is the picture 1 on the right. For this I am just trying to draw approximate figure, and here we know that calcium itself is greater than alkalinity. Alkalinity I am assuming is equal to HCO3 minus, right. So, here this is the total hardness, that is something that we know, but here we see that calcium itself is greater than alkalinity, right. So, what is the calcium carbonate hardness? That is this part. So, that is the calcium carbonate hardness, right. So, that is this part, and what else is left? So, this other part of the calcium will be the calcium due to the non-carbonate hardness. So, that is what we have, right. Calcium due to non-carbonate hardness is the total calcium minus calcium due to the carbonate hardness. And is magnesium associated with any, what do we say, carbonate or bicarbonate? Nothing. So, magnesium carbonate hardness is 0, and magnesium non-carbonate hardness will obviously be equal to, maybe I should have used a different colored ink, will be all equal to the magnesium non-carbonate hardness. So, this can be due to maybe Cl minus. For ease, I am just going to use Cl minus here, right. So, that is magnesium non-carbonate hardness. So, that is the relevant figure here. And what is the other figure that we have? If calcium is less than alkalinity, okay. So, this is the third case. Where should I draw this? Maybe this I am going to draw out here, let us see, right. If calcium is less than, so this is calcium, and let us say this is magnesium, and Ca2 plus and Mg2 plus, right. A lot of questions with respect to stoichiometry and such, but we are just understanding the system. And what do we have here? Calcium is less than, okay, calcium concentration itself is less than alkalinity, but we do not have, okay, I think I understand this. So, HCO3 minus is here, and maybe let me just for the sake of it add here Na plus, and the other part for charge neutrality, let us say it is Cl minus, right. So, what is this case? Calcium is less than alkalinity. So, the calcium carbonate hardness will be equal to the total calcium concentration, that is what you see. And do we presume that there is any calcium non-carbonate hardness? No, it is all used up, right. It is only due to carbonate hardness. And then we come to magnesium carbonate hardness. So, what is the magnesium carbonate hardness? This is this other part that is left out here. So, this is this part. We still have some alkalinity left or bicarbonate left. So, here I have magnesium due to the carbonate hardness, that is equal to the what now? Alkalinity minus the calcium or the calcium carbonate hardness. So, that is what we have, and obviously the other part is going to be equal to magnesium non-carbonate hardness. How do I get that? This I will get by subtracting, okay, this is not until here, I should have drawn this. Let me slightly erase that. I did not see that I had Na plus out here, right. So, let me just redraw that for just a second. So, this is equal to the magnesium non-carbonate hardness. How do I get that? Magnesium concentration minus magnesium carbonate hardness, I will get the magnesium non-carbonate hardness. So, this is how you associate it. Typically, you associate calcium with the bicarbonate or the alkalinity, and then if anything is left over from alkalinity or the bicarbonate, that you are going to use to assign to magnesium. So, first calcium and then magnesium. So, HCO3 and then the relevant anions, but typically in what do we say when we are talking about alkalinity, we saw why we typically refer to it as HCO3 minus, right. So, with that I will end this session, and in the next session we will look at the relevant aspects about how to remove this calcium and magnesium. But at least now you know that you have calcium what do we say with respect to carbonate hardness and non-carbonate, and again same case with magnesium with respect to carbonate and non-carbonate, and we saw the scenarios, right. So, again without extending it further, I am going to end this session.